This video describes several procedures in Statgraphics Centurion version 20 for clustering multivariate data. Cluster analysis is a popular technique used in data mining that groups together similar observations with the goal of identifying hidden patterns. It uses unsupervised machine learning techniques to divide unlabeled data into clusters. Important applications of cluster analysis include healthcare, marketing, computer imaging, and anomaly detection. In this video, I'll describe 5 Statgraphics version 20 procedures for performing a cluster analysis. The first procedure does hierarchical clustering. In hierarchical clustering, you begin by placing each observation in a separate cluster and combining clusters sequentially. The second procedure is the very popular k-means. K-means organizes the data into k-clusters. It assigns each observation to the cluster with the nearest centroid. The third procedure is called DBSCAN. DBSCAN organizes data into clusters based on the local density of observations. It's very good at finding non-convex clusters and also in identifying outliers. The fourth clustering procedure I'll talk about is affinity propagation. Affinity propagation searches for exemplars, which are observations that best represents a set of observations that are then placed together in a cluster. The fifth and final procedure is called spectral clustering. Spectral clustering is a graph-based method for finding non-convex clusters. It transforms the data into a lower dimensional space using the eigenvectors of a similarity matrix. It then applies in that lower dimensional space a standard clustering algorithm like k-means. As an example, we'll look at a popular data set describing characteristics of customers at a mall. The data consists of 200 individuals. Each individual is classified according to their gender, their age, their annual income, and their spending score. Our goal is to group these 200 customers into 2 or more clusters based on having similar characteristics. I'm going to start by describing hierarchical clustering. This procedure has been available in Statgraphics for many years. When you're doing hierarchical clustering, you begin by placing each observation in a separate cluster. You then iteratively reduce the number of clusters by combining 2 clusters into one until the desired number of clusters is reached. The result of this type of clustering is usually shown as a dendrogram. Here you see the dendrogram created for our customer data using Ward's method. I've asked the algorithm to reduce the number of clusters from 200, those are the 200 individual customers along the bottom of the graph, down to a single cluster at the top. The vertical axis shows the distance between the clusters when they were combined. Initially, as individuals were first paired with others, the distance between them was very small. By the time we reduced the number of clusters from 2 down to 1, that's the join at the very top, the distance was about 600. When doing hierarchical clustering, Statgraphics gives you a number of options. The first option is the method to use. I experimented with several methods on this data and found out that Ward's method seems to give the best results. Ward's method chooses clusters to combine based upon finding those that minimize the increase in the within cluster variance. You can make other selections on this dialog box. You can choose a different distance metric if you like. I've chosen the most popular, which is the squared Euclidean distance. You can tell it also that you'd like to cluster variables instead of observations, although that's much less common. Finally, there is an option to standardize the data before calculating distances. Standardizing the data means taking each variable, subtracting its mean, and dividing by its standard deviation. This is very important if you're working with variables that have different units. An important problem when you're doing a cluster analysis is to select the proper number of clusters. In Statgraphics, there are two primary ways to do that. The first is to examine the agglomeration distance plot. This plot shows the minimum distance between clusters when they were combined. To determine the proper number of clusters, you look for a location where large distances begin. The second method is to examine a statistic such as the Calinski-Harabasz index. This index compares the between cluster dispersion to the within cluster dispersion. A common way of selecting the number of clusters is to find that number that maximizes the Calinski-Harabasz index. This is the agglomeration distance plot for our customer data. It shows the distance between clusters as we reduce clusters from 200 to 199 to 198 to 197 all the way down to a single cluster. You'll notice that the distance between the clusters early on is quite small and rises fairly smoothly until we get to 6 clusters. If I go fewer than that to 5 or 4 or 3 or 2 or 1 cluster, the distances start to increase fairly dramatically. The typical conclusion from looking at this particular plot is that the proper number of clusters would be 6. The second way of determining the proper number of clusters is to look at the Calinski-Harabasz index. This index compares the between cluster sum of squares with the within cluster sum of squares. They're each divided by their degrees of freedom, where k is the number of clusters and n is the total number of observations. You can see in this case that the maximum value of the Calinski-Harabasz index occurs at 6 clusters, which corresponds nicely with the agglomeration distance plot. Here is the result of using Ward's method to divide the 200 customers into 6 clusters. The top of the table shows the number of members of each of the 6 clusters and also the percent of all the customers that fall in each cluster. At the bottom of the page, you'll see the centroids, the means, for each cluster and each variable. If you look at that table, you'll see some fairly significant differences between different cluster centroids. Here you see the results of the cluster analysis with respect to two important variables. The vertical axis shows the annual income of a customer. A spending score between 1 and 100 is plotted along the x-axis. You'll notice some distinct groups of individuals, some with low income, some with high income, some with low spending scores, some with high spending scores. There are two clusters, on the other hand, which overlap quite a bit. They are clusters 3 and 4. We'll see the reason for that in a moment. It has to do with the other variable not plotted on this screen, which is the customer's age. This final plot shows a 3D scatter plot of the results of the cluster analysis. You can see spending score along one axis, age and annual income along the other two. You can now see the difference between cluster 3 and cluster 4. Members of cluster 3, it turns out, are much younger than members of cluster 4. This is probably the best plot of the results, showing a pretty good job at dividing this data into clusters. The second clustering procedure we want to talk about is called k-means. K-means groups observations into k clusters with the goal of minimizing the within cluster sum of squares. The value of k is specified ahead of time by the user. The algorithm iteratively assigns observations to the cluster with the nearest centroid, recalculating the centroid after each assignment. When running the k-means clustering procedure, there are a number of analysis options that the user can select. First off, the user specifies k. That's the number of clusters in which to group the data. Secondly, the user needs to select the method for selecting the initial seeds. These are the initial k observations to which other observations will be matched. This can be done randomly. There's a smart selection algorithm that can be used, or the user can actually input the row numbers for those initial seeds. There's also a seed for the random number generator. In any clustering procedure in Statgraphics that involves some sort of random selection, you can ensure that you get the same results run after run if you fix that random seed to a specific value. There's a checkbox that specifies whether the data will be standardized before any distances are calculated. This is extremely important to do when the variables are in different units. Standardization means that each variable has its mean subtracted and then divides the result by the standard deviation. Basically, it puts all of the variables in common scales. There are a number of estimation parameters that can be specified. These control when the algorithm is assumed to converge. And finally, there are options for specifying how to treat missing values. Cases with missing values can be excluded completely, or there are a number of techniques by which missing values can be imputed. Here are the results obtained in Statgraphics when the k-means procedure is asked to form 6 clusters. You'll notice at the top some similar statistics to what was displayed in the hierarchical clustering algorithm. In particular, if you look at the Calinski-Harabasz index, Ward's method could only achieve a value of 128. This k-means procedure achieves a value of 135, which implies somewhat tighter clustering. There's also a Davies-Bowden score and a silhouette score. I'll talk about the silhouette score in a couple minutes. Here you see the 2D scatter plot of the clusters created by the k-means procedure. It's very similar to the clusters created by Ward's method, with one particular exception. You may notice at a spending score of 40 and an annual income of 20, there's a blue point that's now assigned to cluster 1. That point had previously been assigned to cluster 3. Other than that, the results are quite similar. The k-means procedure also calculates silhouette scores. Silhouette scores assess the quality of the clustering by calculating a number between -1 and +1 for each observation. The score compares the average distance of an observation to points in its own cluster compared to the average distance to points in the closest neighboring cluster. The larger the value, the more certain one can be that that observation belongs to the cluster to which it was assigned. Any values less than 0 imply that the observation may have been assigned to the wrong cluster. In our example, the highest average silhouette score occurs when we select 6 clusters. This is the same result as we got using Ward's method. It's also common to create a silhouette plot similar to what you see here. The silhouette plot shows the silhouette scores for each of the members of its cluster. A well-defined compact cluster would show a shape similar to that of cluster 3. You notice that all of the members of cluster 3 have relatively large scores. A less compact cluster might have the shape similar to that shown in cluster 4. There are some large scores in cluster 4, but there are also some relatively small scores. In fact, there's one point in cluster 4 that is below 0. The silhouette plot can be used to pick out observations like that that are worth further study. The next clustering method in Statgraphics I'd like to talk about is called DBSCAN. DBSCAN stands for Density-Based Spatial Clustering of Applications with Noise. There are several advantages of DBSCAN. The first is that you don't have to specify the number of clusters. With k-means, you need to select k, but with DBSCAN, it determines the number of clusters automatically. DBSCAN is also good at finding arbitrarily shaped clusters. The clusters don't necessarily have to be convex. And thirdly, DBSCAN identifies as outliers points not belonging to any cluster. It's therefore often used for anomaly detection. DBSCAN begins by looking for core points. Core points are points that have a minimum number of neighbors, we'll call that min points, within a specified distance epsilon. These points form the core of the clusters. As we'll see, min points and epsilon are set by the user and can be used to tune how the clusters are identified. Secondly, DBSCAN will look for border points. Border points are points which are density reachable. That means they're within epsilon of a core point, but they have less than the minimum number of neighbors to be a core point. Finally, there are outliers. Outliers are observations that are not within epsilon of any core point. When running DBSCAN, the analyst may select various options. The first option is the distance epsilon. That's the distance that defines 2 points as being neighbors. Secondly, there's the minimum number of neighbors required to define the core of a cluster. Thirdly, the analyst can choose different distance metrics if required. Fourth, the analyst can decide whether or not to standardize the data. Again, standardization is important if the variables are measured in different units. There are a number of different algorithms that can be selected that affect how nearest neighbors are determined. The analyst can also specify certain estimation parameters, such as the leaf size if using one of the tree-based nearest neighbor algorithms. And finally, the way missing values are handled may also be specified. One of the most challenging parts of running DBSCAN is selecting the critical parameters. The first critical parameter is min points. That's the number of points required to define the core of a cluster. It's suggested that you start with 2 times the number of variables. In our case, that would mean that min points would be 6. To find a starting value for epsilon, a k-distance graph is often used. If you set min points to 6, then the k-distance graph will plot the distance to the 6th nearest neighbor for each observation. Often that graph will have an elbow. That's a point where the initial pattern, the initial slope, begins to change. In this case, that suggests a starting value for epsilon of about 0.8. Unfortunately, if you use those suggested starting values, you get a fairly uninteresting result. It puts all of the observations except for 6 into a single cluster. The other 6 points are identified as noise. In order to find more interesting results, I started experimenting with different values of epsilon and different values of min points. One of the more interesting results I found was when I set min points to 3 and epsilon to 0.56. In that case, DBSCAN created 4 clusters and labeled 19 observations as noise. The biggest difference between this result and the result from k-means is that a large number of observations were placed into a single cluster. The 3D scatter plot also does a very good job of displaying the results. You can see the 4 well-defined clusters, plus the outliers around the periphery. Here I've elected to draw rays from each observation to the centroid of the cluster that they belong to. One final note about DBSCAN. Unlike several of the other procedures that we'll talk about, DBSCAN does not require the clusters to be convex. It's very good at identifying arbitrarily shaped clusters. Here's the result of DBSCAN applied to a data set consisting of two moon-shaped clusters plus noise. It does an excellent job of finding those clusters. The fourth procedure for clustering multivariate observations that I'd like to talk about in this video is affinity propagation. Now, affinity propagation is an algorithm that creates clusters by identifying exemplars. An exemplar is an observation that best represents a larger group of observations. Exemplars are found by passing messages between observations and potential exemplars. Responsibility messages indicate how suitable an exemplar would be for a particular observation, and availability indicates how available a particular exemplar is. There are two main options that need to be set when you run an affinity propagation. The first option is called preference. Preference indicates how suitable an observation would be to be an exemplar. A lower, that is more negative value, leads to fewer exemplars and therefore fewer clusters. The second option is called damping. Damping affects how much weight is given to new messages compared with old messages. Higher values give more weight to older observations and may lead to more stable results. You can experiment with different values of preference and damping to see which gives the highest Calinski-Harabasz index. After experimenting with different combinations of preference and damping, I found that a preference of -16 and a damping of 0.5 gave a high Calinski-Harabasz index. This is the result. You'll notice it looks very similar to what we obtained with some of the other clustering methods. You can also see from the three-dimensional scatter plot that there are 6 well-defined clusters in the space of the three variables: spending score, age, and annual income. The last type of clustering method I'd like to talk about is called spectral clustering. Spectral clustering begins by creating an affinity matrix. An affinity matrix measures the similarity between two multivariate observations, for example, x and y. By default, a radial basis function kernel is used, defined by the equation shown here. It's basically e to the minus gamma times the squared Euclidean distance between x and y. The eigenvalues and eigenvectors of the affinity matrix are then calculated. The eigenvectors are used to project the data into a lower dimensional space. Then a procedure such as k-means is used to find clusters in that lower dimensional space. This methodology allows very complicated cluster shapes to be found. When running spectral clustering, the analyst needs to set a number of options. First off, the analyst needs to specify how many clusters should be created. Secondly, the method for calculating the affinity between pairs of observations needs to be selected. The choices are using the RBF kernel, a nearest neighbors approach, or a linear kernel. The RBF kernel, as we've mentioned, maps data into an infinite dimensional space, which permits the identification of nonlinear boundaries. The third option that needs to be set is the method for clustering once the eigenvectors are estimated. And finally, if you're using the RBF kernel, there's that critical parameter gamma, which affects how far the influence of a single observation persists. This is the result of using spectral clustering with an RBF kernel and gamma set to 1. As with other procedures, the Calinski-Harabasz index suggests the presence of 6 clusters. Finally, as when using the other techniques, the 3D scatterplot suggests the presence of 6 well-defined clusters. For more information on using Statgraphics for clustering multivariate data, visit www.statgraphics.com.